시작하겠습니다. Okay, hello everyone, my name is Mi and I am graduate student by MEC. So today I will introduce you the journal Quantifying Information Accumulation encoded in the Dynamics of Biochemical Signaling, which is published in Nature Communication in 2021. So let's start from the abstract.
처음에 약간 왼쪽으로 옮겨서 해줄 수 있어요. 끝.
So a distinct sentence.
Second sentence.
Yeah. However, undefined accumulation of information over time to direct cellular decision making remains an unresolved challenge. And I think this abstract is quite clear, and they clearly describe what about the scheme of their method and what system they apply this method. So, okay, let's start. So when there is stimulus given to the cell emits some kind of protein, and we can record the concentration of their protein. So we get some time series or trajectory. But if we give another stimulus, we can have another trajectory. So that means the signaling trajectory has some information of stimulus because we can know which types of stimulus are given depending on the trajectory. And then we want to quantify the amount of information between stimulus and trajectory. And as we know, there is a well-known method for quantifying such information, which is mutual information. So, and for this article, I will use the terminology trajectory, which is almost the same as time series because the author used the term trajectory. So I think all of you guys are quite familiar with mutual information, but for those who are not familiar, I will describe. So this is just kind of one distribution. This is for example, arrival time of lab members. So from this distribution, we can define the surprise of some event. Let's say the event is defined by minus log of that probability. So first consider this event, which is very large count. And for this event, the probability is 12 divided by 24. So if we take the log, the value is 1. So the frequent event has relatively little surprise. However, for this time, let's consider this small event. This is really surprising. And if we calculate the probability, we know that quantitatively this small event is more surprising than the large event in terms of count. So I hope you understand what the surprising in this context. Then we can consider the expectation value of surprise in this whole distribution. And we define this as the term entropy. So at the expectation value, we multiply each surprise by probability and so on. And for each one, you can consider each histogram and calculate each values. And this sum up to 1.92. So entropy means how surprised the distribution, or if you want it, how uncertain, how much we don't know about the distribution. Okay.
So,
Yeah.
what kind of distribution make this uncertainty high, and what kind of distribution make the uncertainty low?
So we can think of the most simple distribution. If we have just one state, for example, just one state, this probability is definitely 1. So if you use the formula, the entropy will be 0 because log p log 1 is 0. But otherwise, contrary, if we think about just uniform distribution, in this case, all the distributions are in the, we can think about n state, and 1 over n is the probability. In this case, the entropy P could be maximized. It means because we cannot be certain where the state will be because they are all the same. So in this case, the entropy is maximized, and we can say this distribution is really uncertain. So, okay, then let's continue. Okay, now we know the class of people arriving each time. So in this case, for each class of people, we want to calculate the arrival, the entropy of arrival for each class of people. That is, we just consider, for example, the postdocs. And there are only 2 states, before Ori and from here. So the calculation is really simple. We just need to add the contribution of 2 states. Okay. And we can repeat for the other classes. So with these values, again, we calculate the expectation value of entropy, but this time we should consider the class. So considering the class, as you see, there are 8 postdocs and 9 graduate and 7 interns. And these are the range. So this value is 1.414. And as you see, this is value is smaller than the original entropy. So as we know the class, the distribution becomes less surprising. It becomes clear relatively. That means class have some information about the distribution of arrival. So we can now define the term mutual information of arrival and the class. This is just the difference between the original entropy and the entropy after we know the class. This is, I think, very intuitive definition. Okay. So, okay, more in general terms, if we consider 2 variables, x and y, we can define mutual entropy as the difference, and conveniently they are symmetric, so we can use Bosch formula, which is, and what we need is for this calculation, we need probability distribution of x, y, and the conditional distribution of x on y, or vice versa. Okay, now let's get back from this example, the cell signal trajectory. For this, we want to calculate the mutual information between trajectory and stimulus. So first we need the probability distribution of trajectory and the conditional distribution, the trajectory over stimulus. But however, unfortunately, there are some challenges for estimating those probability distribution. So I will introduce what are the challenges. Any questions? Okay, then, I told you we need probability distribution, but we usually do not know the true distribution. So we just sample from distribution. So when we have just little of samples, the estimation will be very inaccurate. However, if you have many samples, it could be accurate, the estimation. So the problem arises when there is so many possible states, however, we have just limited number of observations. This makes the estimation very inaccurate. Now, for our time series or trajectory data, for example, there are 5 states for each day, arrival time, and the path for weekly trajectory, just 5 days. From Monday to Friday, there will be more than 3,000 states. So, unfortunately, we don't have so much lab members. So, we cannot do that directly, but we can give some assumption to simplify the situation. One strategy is we treat each day as independent. That means we estimate from Monday distribution and Tuesday distribution and Friday distribution. And just if you want to know one set of probability, we just multiply them because we treat them as independent. This is one of the simplest approximation for estimation. So, however, there should be some problem. This is too unrealistic. By saying that we assume temporal independence, we can say we ignore temporal pattern. That means, for example, if we want to consider oscillation, this is some oscillating trajectory. By ignoring pattern, we just shuffle, and this becomes increasing pattern. We don't know these are not really the same response of some biological systems. So, in sum, for estimation of probability distribution, especially in trajectories, we cannot estimate all states. It is too much compared to our observation. And we should consider the temporal pattern of the trajectory. So, to resolve these challenges, the author introduced in the very famous model, hidden Markov model. Okay. So I will briefly introduce what is the hidden Markov model and hidden Markov model. Okay, let's just say we have some trajectorial Dale from Dongju's paper, and if yesterday I am happy, according to that trajectory, the probability today's happiness is 2/4, whereas sadness is 2/4. And similarly, if yesterday I was sad, today I will be happy, probability of 1/4, and similarly 3/4. So that means we can make some matrix, which is called transition matrix. So this constitutes the so-called Markov model. This model is the transition depending on only the yesterday's or previous time. So somehow we partly consider the temporal pattern for our model. Now, the state mood could be hidden. It is hidden because we cannot see other people's mind. And in this case, instead, we can observe something not hidden. Okay, for example, time of sleep. Early or late. And then, as before, we can know the transition matrix of the hidden stage. And this time, we consider the so-called emission matrix, which is related to observation. Okay, if you see this table, if you are in hidden state, if you are happy, you can count the number of early sleep. So this probability will be 0.75. And similarly, the probability of late sleep. And we can do this for the hidden cell state. So by attaching this hidden state, this is so-called the hidden Markov model. Okay. Then I will not discuss this today, but such transition and emission could be estimated by Baum-Welch, so very famous Baum-Welch algorithm, which is based on maximum likelihood. So for this algorithm, the number of hidden states in observed states are in fact hyperparameter. That is what we should estimate and we select. So anyway, by that reason, we somehow restrict possible number of states. Okay. So let's say we have the transition and emission matrix and emission problem. Okay. Let's introduce it in notation. If the hidden state is happy, we can say the probability of emission state is observed state is early. And similarly, the transition probability, PT, is yesterday if sad, what is the probability of today is happy. So if we consider this trajectory, early and late, the probability of early and late would be, first we consider the emission probability, and second the transition, and multiply transition, and lastly again emission. Okay. So similarly, if we extend the series, as we already know the pre-part, and again the transition, multiply transition probability, and lastly multiply the emission probability. So this is what the authors call trajectory probability.
어려운데? 잠깐만 천천히 해봐.
네.
Everyone understand this?
So okay, let's start from here. Okay, assume that we want to calculate the probability of this E and L. The trajectory EL. Trajectory EL. So first we need to consider the emission from happy to sleep early. And then we multiply by the transition, which is happy to sad. And for the lastly, there is another emission from sad to late sleep. So this will be
The clear part is that we only consider the probability of
Yeah.
observing this EL time series.
Yeah.
But This calculation is based on, we assume that we already know the hidden
Yeah.
mood state.
So for that part, so I told you that this state and this probability are estimated from boundary algorithm. So based on that, we can select this hidden mood as the maximally likely state.
Here we assume that we already know the
Yeah.
whole
Hidden
state.
state following that algorithm.
Here we assume that emission probability and transition probability.
Yeah.
So emission probability means hidden to the observed, and transition means between the hidden.
Yeah.
Right, top two. Under the assumption that we know that two type of probability, we can calculate the trajectory probability.
Yes.
That's what. Is it clear? If we know emission and transition.
I think we also need to know the hidden mood state.
Oh yeah. So for this calculation, we should determine this hidden state, right?
Is it determined from the previous
Yeah.
algorithm?
Yeah.
Then that is clear.
Which is based on maximal likelihood. So okay. Now anyway, we know how can we calculate the probability of trajectory. So let's summarize. We have some experimental data, which is cell signal 23, and then we train the hidden Markov model. Using this model, we infer the probability of each trajectory on each stimulus. Now we are trying to quantify the information between trajectories and stimulus. Okay, mutual information. Okay, please recall that for that mutual information, we need to estimate first probability distribution of trajectory, and then trajectory condition of the stimulus. Okay, we know this game because in experiment for each stimulus we get trajectory, and we have the probability from hidden Markov model. Okay, this part is okay. Now we need to consider that part. How about not considering stimulus? For that part, we could use Bayes' rule, which is just the trajectory, probability of trajectory can be known from this conditional distribution and the prior distribution. However, there is problem. We don't know the distribution of stimulus because just experimentalists control which stimulus they will give. So instead of estimating the stimulus, we just take the simplest approach. We choose the set of probability that maximize their mutual information. So for example, if we have 3 stimuli, we just pick some combination of probabilities that maximize mutual information.
Choose P. So I mean the P1 to the Pn is probability for stimulus.
Yes.
You want to maximize mutual information between
Trajectory and stimulus.
So just you assume that stimulus will be given in a way to maximize the MI.
Yeah.
Any reason?
I think there is not a very clear reason, but
opinion that the definition of probability of stimulus is quite confusing because, as you said, the experimental method control the stimulus.
Yeah, so I think so.
Can we also just uniform because that's what they did in experiment? I don't know.
But
What is natural for everyone?
but I think if for this case, the experimental is continuous. But in natural situation, the cell will encounter many stimulus, and their distribution would be something. So I think that will be more natural condition. Yeah.
Do they define what is a stimulus in their case? Like, do they specifically focus on one kind of stimulus, or can it be any kind of stimulus?
Yeah, they chose some few stimulus conditions, like chemicals, kind of types of chemicals.
Okay.
Yeah.
Anyway, let's believe it. They maximize it.
Okay. Now I will show you the result of the experiment. So for the experiment, they consider the NF capability cell, and they gave stimulus. Okay, I don't know what they are. So they get, for each stimulus, they get the trajectory. If you look at the trajectory, we can simply think that, for the first part, they're very similar, their response is similar.
Now you apply.
Yeah.
Okay, before can you go back? Yes. Yeah, one more time back. So just anyway, in your previous explanation, we have, if I remember correctly, we said we need to know emission probability and we need to know transition probability.
Yes, yeah.
And then how they infer both probability.
The part is on the training hidden Markov model. Because
I see. I see.
yeah.
What do you mean that now probability ELL is? Then can you go back?
Okay.
Here, I see. So trajectory is given.
Yeah, trajectory is given.
So that means left side probability ELL is given.
Yeah.
Using that, you want to infer the emission and transition probability. Kind of. Yeah. I think that part should be very clear. What is the meaning of train HMM? What is known and what is unknown?
Okay, for this case, you can only observe the time of sleep,
Yes.
right? But we don't know the hidden state.
Yes.
So for the hyperparameter, we fit them the number of hidden state. And yeah, so depending on the number of hidden state, you can use the so-called bound-mesh algorithm.
Yeah, it could be 3 or 4, it doesn't matter.
Yeah. So
But anyway, we don't know the transition probability, we don't know the emission probability.
yeah.
Okay?
We don't know mass, but okay, the
Bound-Welch algorithm is that you mean the training Markov model.
So yeah, I think it's better to draw something. Let's say this one is observation. And we don't know hidden. Okay, we can hidden here. We can like say this could be happy, sad, happy, or this could be sad, happy, sad. There could be many choice of hidden state. However, for some combination would be more likely than other combination.
Solely from E and L time series,
Yeah.
we infer transition matrix, emission matrix, and even the trajectory of hidden state.
Yes.
That's what the bound will show.
Yes.
I don't think hidden time trajectory doesn't matter in this. So the key point is what is observed,
Yeah.
what you want to infer. That first, let's think about that first. What is given?
Yeah.
Trajectory of
In this case, sleep.
sleep. And then what do we have to infer?
The first is the transition matrix
Yes.
of hidden state and their emission probability.
Yes, there are 8 numbers. But don't think
yeah.
about it's a series. It's
Yes.
very easy problem.
Yes.
You have that time series data E, LE, LLLE.
Yes.
Okay, everyone. And then there are 2 matrices. One is a transition matrix, another is emission matrix. Okay? If we have that 2 matrices, can we generate the time series of the E, LLL, blah 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 thing? Yes. Can we? Look, just think about it. Let's make very extreme. 1, 0, 0, 1. Let's make very extreme. 1, 0, 0, 1. What that means? Hidden state
all smile.
never change. 1, 0, 0, 1. If we choose that matrix, what kind of trajectory we can make?
E or L.
E or LLLL. Do you think that's correct? Can we reproduce this? No. Then that matrix will not be chosen. Anyway, we want to choose some numbers here under which condition generated trajectory is similar to this observed trajectory. Does it make sense? There are 2 control we have. Some change between hidden. And then of course this hidden can be not always early, not always late. It has some probability. Then by choosing this A number, what would be the best to reproduce that given observed trajectory? Does it make sense? Now why this is good? Do we mess up the trajectory? Kind of the first thing Kangmi mentioned, we mess up the oscillation, blah blah. Here, this temporal transition is important or not to infer this information. Just think about it. EELE or EEEL. In these 2 trajectories, inferred number will be same or different. It'll be different. So we really use temporal structure to get the point. So, but why this is very smart is, for the given trajectory, it changed the problem to estimate the just 2 matrices number. It's very similar to you fitting the ordinary differential equation. There is trajectory. Underlying the trajectory, you can write the certain differential equation, right? That differential equation has coefficient or not. How do you choose that coefficient of differential equation? Which minimize the simulated trajectory with observed trajectory, right? In that case, do we mess up the trajectory or not? We maintain that, use the trajectory, right? Same. Rather than ordinary differential equation, we use this matrix. It's easier than ODE. In this room, everyone has experience of ODE fitting, right? Correct? Rather than ordinary differential equation, we will use much simpler. Think about it, this is just dynamics equation. ODE and this matrix, which is simpler? This. It has just two states. Very simple, just four number. Actually not four number, right? Sum is 1, 1, 1, 1. Yeah, how many? Just two number. We'll make a decision for this dynamics, that's all. Okay, but currently say we need to determine either 2 or 3 hyperparameter. Okay, but of course I expect from the small number of states, if it work well, we will stop. If it doesn't work well, then we'll change it to the 3 state, isn't it? Isn't it similar what you had done so far with OD? Olive? When you do the epidemiology model, what you did? You begin with a very simple OD model and you try to fit it. If it fits it, fail, what do? You make the equation is more complex. We call that hyperparameter. Is it clear to everyone what is a hidden Markov chain thing? It's not that difficult thing at all. It's more easier than what you did. Okay? For the statistician, ODE is very difficult. That's why they use this simple matrix. Because this one, differently, you learn this at the high school matrix class. Do you remember? 고등학교 행렬 시간 이런 거 배웠을 텐데. 안 배웠나? 우리 때 배웠는데. In high school, did you learn about this or not? The probability. Did you know?
배웠습니다.
You're old. 하이스쿨에 내가 안 가르치나 했지.
일단 행렬은
이제 다시 배우긴 하죠. 그때는 없었어요? I see. Dr. Wang is younger. Okay. Good. Yeah. So anyway, that's not. Don't think this is serious thing. Just there is a matrix, and then you just fit that matrix number to the given data. Because with the matrix, can we generate the trajectory? Yes or not? Yes. But that trajectory is not deterministic. It's just because there are many. But anyway, I expect that the average should be similar to what we see. That's what we call maximum likelihood, I guess. Is it clear now?
Yes.
Okay.
Thank you.
So,
Okay.
then here what they mean is there is experimental data. There are bunch of trajectory, right? And there they can train the HMM means. What that means, there are metrics for the transition matrix and emission matrix. We fill the number for the transition and emission matrix. And then here, infer trajectory probability, what that means. And if we know these two matrices, what would be the meaning of that infer trajectory probability?
Just use that matrix for multiplication.
Then, Kangmi, can you go back? That trajectory probability formula. Here, yes. If we know the 1, 2, 3, then we can calculate the probability of E and L. And in this way, we can calculate every trajectory's probability. If we know that two matrices match. Clear? Everyone is okay?
And then
Good job. And for trajectory probability, we are happy. Okay. But problem is, so far from trajectory, we reach here, and then we calculated. But this is known, right?
Yeah.
Per given stimulus, we know this trajectory is 0.2. We know the 0.3. But actual trajectory, because we don't know this, so we do something here, but we are uncertain here. And then let's see why they did. Actually, I don't know why they need this differently. That's why I'm confused. But am I clear? From the hidden Markov, we reached to here, right?
yes.
Everyone is okay? And then here we make some assumption. Then for given any trajectory, we don't know the stimulus information.
What I'm confused is that so we may say that to calculate the trajectory probability,
Yeah.
we need to train the
Hidden Markov.
Markov things. Then the conditioning of the stimulus means that do we train the transition matrix only for each trajectory or using whole trajectory under that stimulus?
Under the stimulus. For all trajectory under the stimulus.
뭐 지금 걱정되는 거예요.
그러니까 저 probability 스티뮬러스에 컨디셔닝된 트랙토리 probability를 구한다는 거거든. 스티뮬러스 하에서 옵저브된 트랙토리 전부 다 모아서 히든 마코브를 학습을 하고 저걸 계산을 하는 거죠. 그러면
스트레치가 여기 일단 스티무러스가 두 종류가 있지.
그러면 저 빨간색만 모아서 하면 저 중간에 있는 값 하나가 나오는 거고 파란색만 모아서 하면 또 중간에 있는 값 하나가 나오는 건데.
그렇지. 그러니까 I think using this one, only red one,
Yeah, on the red one,
they train
training one
to get calculate this.
Yeah. Okay,
And then using this blue one, they I think train again because the stimulus, depending on the stimulus, hidden Markov chain should be different, isn't it? Dynamics will be changed. Kind of, my understanding is ODE. We have ODE, but we change the stimulus. Then ODE change or not? Change. So that's why I thought that hidden Markov chain should be also changed. So my understanding is this training should be red part, blue part too, independent. But anyway, no matter what, independent or not, we can calculate this, isn't it?
Yes.
But the problem is, when this trajectory is given without this is red or blue, isn't it? If we don't know this is either red trajectory or blue trajectory, what is the chance of that trajectory? Without knowing the stimulus. We have no idea, right? How to do it is, what they did is, if stimulus 1, what is the chance of that trajectory is observed? Plus, when stimulus is second time, and what is observed at that given trajectory. But how much we weight is under this some maximized. I don't know, but that part is unclear. But it depending on the goal of this project, let's see. Is it clear? So let me explain one time. This trajectory is given, okay, but we don't know stimulus. How can we calculate the chance of this trajectory? we don't have a hidden Markov chain model for this. So we assume it stimulus 1. Then do we have hidden Markov chain? Then can we calculate the trajectory? Then let's say the probability 0.3. For stimulus 2, we can calculate it, right? 0.5. Then how to merge? Assume a certain weight. We can do the average, then this trajectory's probability can be estimated. Up to here, okay. But this part is only unclear so far. Happy? Move on. Yes.
Okay, with this choice of stimulus probability, they calculate the maximal future information. Anyway, so we have the some biological system and we give them stimulus, two kinds of stimulus, two,
Okay.
and then they get
Two trajectory.
ensemble of trajectories, and when we look at this with our eyes, for the first part,
Same.
they are really similar. So we may think that, oh, this is less informative. And for the late part, we may think they're really different. This part will have more information. So let's quantify this. We can calculate the mutual information. So first, if we only use the formal part for the mutual information calculation, we have very little information which we expect from our look. And if we see the later part, if you use the full trajectory, this value rises. That means, the stimulus can be easily distinguishable after the 6 hours.
So is that mutual information is calculated
Based on trajectory.
Yeah.
some coded time trajectory,
Yes.
and as x-axis value increases, that means it uses
The
longer.
longer trajectory.
Okay. Then here is a jump to me. So far we did our best to calculate that trajectory probability.
Yeah.
Why was it needed to calculate that much? Now you suddenly talk about the mutual information. Here, so far we talk about in the board how to calculate the probability of given trajectory, right?
Yeah.
Why now you jump to the mutual information? I know you explained in the early.
Yeah.
Now you need to add it here if you give a talk at the conference. Let's go back. Here is a gap. So everyone is very important. I know in this room, majority people have written the manuscript with me. What they break here. Dr. Wang, you recently learned. We talk about the trajectory. Now we talk about the mutual information. Old and new rule is broken. Then people cannot understand. So to calculate the mutual information, what do we need?
We need the
Probability distribution of trajectory.
Yeah.
We need these two. Calculate the mutual information.
yes.
Okay. Then tell me. Okay. Then although I know you say this, no one can remember this.
Yes.
Okay, let me give a talk. For example, to calculate the mutual information from the trajectory, what we need is probability distribution of a whole trajectory. And then we also need conditional probability of trajectory for given stimulus. We need 2. But both are kind of, what is the chance of this trajectory? Is it easy or not? What is the chance of observing this trajectory? It's not easy. If it's not trajectory easy, think about it. Just thinking of this end point, only we have one snapshot. From end point, can you draw the distribution? 3, 2, 1, 5, 6. Can we calculate the distribution? Easy or not? Very easy. Elementary school, right? But just think of if you have 2 points. Now if you compare, but in the order, now it become complex, right? Already. One way is, okay, let's draw the 2-dimensional heat map. First component and second component, maybe you can imagine some distribution. Okay? But how many points do we need? A lot. Now we have 100 data points. So time series is 1 point in 100 axis dimension. To calculate the distribution of that, how many trajectories do we need? How many? Unbelievably many. Impossible. Okay? So, that's why from the trajectory, knowing the probability is very, very difficult. What is the chance of this observed trajectory? Can you imagine? It's very challenging. So rather than calculate the probability in a rough way, what we will do is, we will try to understand the governing equation. If we know the governing equation, it's equivalent to knowing infinite number of trajectory, isn't it? If you have ordinary differential equation with the known coefficient, how many trajectory do we know? As much as we want, isn't it? So that's why for the trajectory, it's a super high dimension. Calculating the distribution is, just calculating distribution is impossible. So then what we will do is, we'll first find the governing equation, and then using that equation to get the infinite number of the trajectory and generate the probability distribution. Does it make sense? Good? Happy? Okay, so that's why from this trajectory, it talk about the hidden Markov chain training. Okay, so to know that governing equation, we will do the hidden Markov model, and then we will train the hidden Markov chain, then we know the equation, so that now we know all the trajectories and conditional distribution, so that by merging these two and using this formula, we will calculate the richer information. But anyway, today's is one key message is what? What should be key memorized? Number one is difficult. Calculating the probability of trajectory is not easy. How to usually calculate the probability? Flip the coin, right? But trajectory, we can't. We have to know about the mechanism of the coin first. That's a hidden Markov chain. Happy? Does it make sense? Okay. Then let's go. Okay. 아, 그래서 저렇게 스토리가 흘러간다고? Okay.
Okay, I show you the results. So with this model, we can specify when is the critical point for
야,
the
근데 그냥
difference.
눈으로 보면 되는 거 아니야? 설마 저걸 위해서 이걸 다 했다고? I don't know. Do we really need this mutual information? In my eye, yeah, we have to do it after 6 hours. Yes. Look at the raw data. Can you remove that red and blue box? Can you remove the red and blue box? 애니메이션 아니야? 처음부터 있었던 거.
이거 그래 꺼져가지고.
야, 너무 충격적인데? Everyone look at it. Up to which time top and bottom can be distinguishable? Can you see? What time? Maybe, yeah. Up to 4 nearly the same, right? around 5 or 6. 이게 끝인가?
얘가 제일 중요한 거야. 그러니까 얘는 결과보다 메소드를 좀 중심인데.
소가 이게 얘들이 개발한 거라고?
사실은 원래 있었던 메소드 하나 살 그 히든마크를 붙인 게 얘들이거든요.
아,
원래
그러니까 히든을 하나 붙였다고?
네.
Okay, so, but there, I know the conclusion is very trivial, I don't know, we need that kind of weapon to be frankly. Anyway, their conclusion is, okay, we can distinguish these 2 signals from 6 hour. Da. Kahi, can you distinguish this 2 signal after 6 hour? Correct? I don't know yet, the result is not that exciting, but anyway, Kangmin said the method is, but previously people didn't use the hidden markup, they just
Yeah.
used, I see. What Kangmin said is, previous approach is, to calculate the trajectory, what can we do is, rather than consider the hidden dynamics, we can directly consider the Markov chain between E and L.
previous method didn't even use Markov model.
Oh, really?
They just assumed that previous independent dynamics.
Independent dynamics, I see. 약간 너무 심한데? 그거 약간 사기인 것 같은데, 이 말콤 체인이 동주가 없으니까 이거 안 된다 근데 이거 너무나 익숙한데.
동주가
한번
그러니까 여기 연구실 들어가서 처음에 해보려고 했던 게 이거 아니었어요?
이게 언제 동주지?
21년 뒤.
동주가 이걸 보고
어떤 거요?
그막 히든 맞고.
그건 제가 안 했어.
그렇지, 넌 뭘 보고?
이런 거는 전에 나왔어요.
서프라이즈 이걸로 네이처 컴퓨터라고? 오케이. 일단 가봅시다.
네.
Surprising.
Okay. So this is the last part of the result. So I will give you the summary.
진짜로? 이렇게 한다고?
따질까?
어.
네. Okay. So I will give you the summary. Okay. As you saw, the estimating of probability distribution of trajectory is really challenging because we should consider the temporal pattern and there are too many states. So the author utilized hidden Markov model for the estimation of trajectory probabilities. So with this new method, they could quantify the stimulus dependent on different cell signaling trajectories. Okay. If you have any question, please ask.
Any question?
Yeah.
I have a simple question. So in the paper, they said that they proposed the dynamical mutual information. Is it a new thing or is their own?
Do you mean the terminology or
I
terminology?
mean, not just the terminology.
This concept.
그러니까
This concept is trivially
너무
suggested.
많아서
But
So they just named it.
yeah, dynamic mutual information is named by them.
But it was used already before.
Huh?
The concept is already used before.
Yeah,
일종의
they just
말하자면
improved the concept. Actually, to be frankly,
우리가 데이터 길이가 긴 게 필요하다.
I think it went to Bacon because the previous paper was
데이터
silent.
디스트리뷰션을 구해야 되기 때문에
Yeah, so I think there is some historical reason.
히든 마크 체인에 거기가 들어있어. 근데 숫자가 정확해.
So, any questions? Yeah, okay.
뒤에서 그
Probably a stupid question, but I'm kind of blocked about like the hidden state and their transition.
Yeah.
I have not really understood. So, do we know this hidden state beforehand? Is it like some a priori knowledge we learn about the system?
It should be as invert from observed state.
Okay.
텐스파인
And
스트로킹은
that inference is based on the statistical method, maximum likelihood.
정보가
which-
줄어들느냐를
We determine mostly likely hidden states.
And is it the same for the transition? Because in your example, you take
Oh, yeah.
happy and sad.
다른 필터를
It is same for the transition.
받느냐.
Okay, okay. But
그래서 느낌이 조금 다르긴 한데
How do they eliminate some possibilities? Because I assume that there would be like the number of hidden state and the number of transition must be.
Sorry, I missed the former part.
So I'm thinking like the number of hidden state and
Yeah.
transition must be very huge, right?
Yeah,
So
yeah.
how do they limit the possibilities?
They start with small numbers and increase the number of passive state,
Uh-huh.
and they use like information criteria, such things, to determine the optimal number of hidden states.
Temporary transition then?
Always.
Okay, thank you.
Any other?
Questions?
Yeah, thank you, Min.